In many chemical reactions, one reactant is used in excess. The one you run out of first is your limiting reactant. So imagine we have a barbecue, and I buy 100 hamburger buns at the bakery. Then I buy 100 tomatoes, and I buy 100 pickles, and I buy 100 onions, and I buy 10 gallons of ketchup, 10 gallons of mustard, 10 gallons of mayonnaise. And then I buy 3 all-beef patties. How many hamburgers can I make? I can make 3 hamburgers, because after I've made my third hamburger, I'm out of beef patties, and that's a key essential ingredient in making a hamburger. And it doesn't matter how much ridiculous amounts of extra stuff I have, if I'm missing one key ingredient, I can't make any more hamburgers. And so that is the limiting reactant. Because we ran out of an essential ingredient, that limited how much product we could make. And the same thing occurs in chemistry. The limiting reactant is the chemical you run out of first, and because you run out of it, that limits how much product you can make. Basically, the reaction stops once you've run out of the limiting reactant, regardless of how much extra other stuff you have. Here we have an example with bicycles. If I have 8 wheels, 4 frames, but only 3 pedal assemblies, I could only make 3 bicycles. Because even though I have extra wheels and an extra frame, I'm out of pedal assemblies, and that is an essential component of a bicycle. And then once I run out of that, I can't make any more bicycles. So, if you start with 5 molecules of hydrogen and 3 molecules of chlorine, how much hydrogen chloride could you make? Well, they react in a 1-to-1 ratio, and you produce 2 HCl's for every 1 chlorine or every 1 hydrogen reacted. We can make 6 HCl's. Because if all 3 of our chlorines react, they'll react with 3 hydrogens and make 6 HCl's, and I'll have 2 molecules of H2 left over. So the chlorine is the limiting reactant. Once I've used up my chlorine, it's gone and I cannot make any more HCl. The hydrogen is the excess reactant because I have 2 left over that I can't use. When you're trying to figure out which chemical is the limiting reactant, work it all the way through for every reactant. If you're given so much of A, figure out how much product you'll make. If you're given so much of B, figure out how much product you'd make if it all reacted. The reactant that gives you the least amount of product is your limiting reactant. So how many moles of hydrogen chloride can be produced from 4 moles of hydrogen and 3.5 moles of chlorine? Well, if all the hydrogen reacted, it's in a 2-to-1 ratio, I could make 8 moles of HCl. If all the chlorine reacted, I could only make 7 moles of HCl. Therefore, chlorine is the limiting reactant. When you work out all the reactants, the one that gives you the least amount of product is your limiting reactant. Because once I've made my 7 moles of HCl, I have no more Cl, and I cannot make any more HCl. How many moles of magnetic iron oxide? That's kind of a tricky one, F3O4, because the charges don't make sense on first glance. Fe3O4 is actually a 50-50 mixture of iron 2 oxide and iron 3 oxide. We call it magnetic iron oxide for short. So it's FeO dot Fe2O3. So it's 50% iron 2 oxide, 50% iron 3 oxide. And that's where you get the Fe3O4. So how many moles of magnetic iron oxide can be produced from 16.8 grams of iron and 10 grams of water? You can never go by grams because different chemicals weigh different amounts. And so the grams doesn't really tell you how many molecules you have. And also, things are used in different ratios. So just because you have more of something doesn't mean you might run out of it faster still just because you're using it faster. And so you always have to work it all the way through and figure out how much product you're going to make if all of the reactant reacted. So if all the iron reacted, we convert it to moles, and I make 1 mole of magnetic iron oxide for every 3 moles of iron consumed. Let's make sure it's a balanced equation. 3 iron on the left, 3 iron on the right. 8 hydrogen on the left, 8 hydrogen on the right. 4 oxygen on the left, 4 oxygen on the right. It is balanced. And so we could make 0.1001 moles of magnetic iron oxide if all the iron reacted. If all the water reacted, I could make 0.139 moles of magnetic iron oxide. Therefore, iron is the limiting reactant. Even though you had less water, water's a lot lighter than iron, so you actually had a lot more molecules. And the water was used a little bit faster, but not fast enough, and so you run out of iron first. And so again, because of that, that's why you always have to work it all the way through and figure out how much product you would make if every single one of the reactants was totally consumed. And then the one that makes the least amount of product is your limiting reactant. How many grams of silver bromide can be produced from 50 grams of magnesium bromide and 100 grams of silver nitrate? And how much of the excess reactant remains? Well, let's work through both reactants. I convert my 50 grams of magnesium bromide into moles. Again, I get the molar mass by adding up a magnesium and 2 bromines. And it's a 2-to-1 ratio. I produce 2 moles of silver bromide for every 1 mole of magnesium bromide consumed. Convert back to grams, I can make 102 grams of silver bromide. If all my silver nitrate was consumed, I can make 110 grams of silver bromide. And again, now we have a 2-to-2 ratio. Oops. Because I use 2 silver nitrates to produce 2 silver bromides. So 2-to-2 stoichiometric ratio. So less product is formed with the magnesium bromide, so that is my limiting reactant. I will use up all the magnesium bromide. So the next question is, how much silver nitrate would be left? Well, if all the magnesium bromide is consumed, and now my stoichiometric ratio is 2-to-1, I consume 2 moles of silver nitrate for every 1 mole of magnesium bromide consumed. Then I convert back to grams. I would use 92.3 grams of silver nitrate. If we go back to the beginning, you started with 100 grams of silver nitrate. And we only used 92.3 grams, which means we used up all the magnesium bromide, and we have 7.7 grams of silver nitrate that was not used. It is the excess reactant. It was not used up. There was stuff left over when all was said and done. How many grams of barium sulfate can be produced from 200 grams of barium nitrate and 100 grams of sodium sulfate? Again, work them both through. Convert grams to moles, and again, the molar mass of barium nitrate. You have 1 barium, 2 nitrogens, and 6 oxygens. And it's a 1-to-1 ratio. We produce 1 mole of barium sulfate for every 1 mole of barium nitrate consumed. Convert back to grams. A barium, a sulfur, and 4 oxygens is 233.4 grams per mole. And we get 178.6 grams product. You run through the sodium sulfate, we convert it to moles like chapter 7. Now it's a 1-to-1 ratio because it's 1 sodium sulfate to 1 barium sulfate. Convert back to grams, we get 164.4 grams because consuming the sodium sulfate produced less product, 164.4 grams as opposed to 178.6 grams. The sodium sulfate is the limiting reactant. And let's double check and make sure it was balanced. 1 barium, 1 barium. 2 nitrates, 2 nitrates. 2 sodium, 2 sodium. 1 sulfate, 1 sulfate. It is balanced.